Okay, start off with here. I'm going to give you a few minutes to work on this problem. Not a whole bunch. I don't expect you to solve it all yet. This is mechanical, right? Remember, we touched on a problem. I'm giving you some information here. Ambient 95, head pressure 240, suction pressure 50. My suction line temperature was 50, liquid line was 95. I'm using R22. I have a fixed metering device. It's a 3-ton AC, 10 SEER, and compressor amps are 16. So, with that stuff you would have gathered in the field, I expect you to construct it with chart like we did the other day. Head pressure, suction pressure, superheat, subcooling, and draw. Got my expected on top, my actual below it, and then my direction. All right, now I know we went over it once. Most people get stumped, but this is an opportunity to kind of see if you can remember what we did, how we did it, where we're going with it. Okay? Let's see. Showing up pretty good, are they? I'm sorry. No, we got used to the other light again. I mean, although it doesn't seem to be pretty that dark either. Sorry about that. Everybody have to move to the front.
Obviously, we're not Baptists. Everybody read it now? Is there still anything?
Yeah, let's do it. He doesn't have me. Oh, there it is. What does he want to use, the 30 and 30 or add the 20?
22. He said systems was found to be 30.
I got 275 for expected temperature.
So theirs is 278.1. That was just 278.
For 125. Oh, okay, yeah, that's right. This doesn't have, yeah. This one doesn't have 125. Oh, yeah.
Yeah, two seven eight, R22.
No.
It's 278.
It goes from 124 to 128.
Yeah, it's 278.
Yeah.
So we don't have a chart like that. I don't know where I did my chart like that.
Well, that one hits it on the head. This one goes from 124 to 128.
So it's 278 you put right there.
Yeah, 278. The temperature.
Okay, temperature. And then you know, on R22, 278. Oh, you said yeah, R22. 50 degrees. Like you look at 275. The first one would be dang. 50. That what you got? So 275.
Well, 278. It's exact over here. It goes to 125. My chart.
So you get 119.
How do we get the expected suction?
R22 would be, oh, you said 40, 68.6. Yeah. What do you got?
You got 50.
You got 50 up there. So that'll be 50. So it's 50.
You said 68 for 40?
Yeah, for 40. But this one for 50, it's 84.1.
I know, but that's what he got. That's the extra.
Yeah.
The speaking is.
Oh, yeah, because that's temperature.
Yeah.
But it's got pressure, 50 pressure.
And sugar pressure is
Suction.
Yeah.
suction pressure.
He's got the suction line and the liquid line.
So
Liquid line is 95. Yeah.
You said 68 for 40?
For 40 is 68. 68.6, like 69.
What is 40 matter?
That's the core temperature, what he gave us on the board, remember?
He always wants it to be 40. Right?
Yeah, after it runs at 40 degrees. That's right. I got that right here.
So you go 68.6.
So we're down.
So
69.
Arrow down.
It'll be down. See, yeah, he said run on 40. That's what I got on my paper. I always run on 40.
So your SH is the, yeah, so it's section line temp minus the section pressure temp.
So you have to go up and get this thing again up there.
So you do 69 times 50. Right? 69 times 50. I
Yeah,
say
you got 69 on 50.
yes. So it's down too.
It's up.
What do you say?
That's 19. It's supposed to be 520.
Yeah, that is.
Remember, if the higher temperature is,
Yeah, it's supposed to go.
yeah, if the number is higher on top, then it's down.
This one right here, this one says it's supposed to be 512.
Yeah.
If it over 12,
Oh, yeah, that's right.
you go up.
That's right, you're right.
So now you making sense with me.
Yeah.
The expected on super, he was 5 to 12, right?
Yeah, he's right.
You put 5 and 12 on the station, you actually put 19.
And then 10 to 12 on subcooling.
Yeah. So cool is 10 to 20.
10, 20.
10 to
10
20.
to
Yeah,
20.
10 to 20.
So you put 10 to 20 in that box. And then you subtract. Now pressure temperature.
Liquid line. We gotta get pressure to 240.
You got to convert something.
Temperature for
You gotta convert the temperature to 240 and then subtract it.
11 is, or 114 is 240. What is this chart?
Right. 114. That's 115.
So it's, sideways. 19, I got 19 degrees, let's see.
So you put it at 115 from which?
That's 20. That's good, but it's within it.
Right at 20. And then the last one is action. 16 or what? Amps. Just amps. 16. It says 16 number 4. Yeah. Who do you see that on the bottom? Oh, that 16 on them. Can't see it for real.
I think he said it's 7 amps per ton.
I got wrote down. I didn't get that. I just got, like you did, like 14, 10, and then that.
I think he said 7 amps per ton.
It is 7 amps.
Yeah.
Yeah.
So 21 amps is what it should be.
3 times.
Should be, expected amps should be, 21. You know, reported 16.
So that's low. So what's this? 21. So that's 21, you had to add 7 to the 16.
It's 7 amps per ton, so 3 times 7. Then half amps you get up to 16.
Here comes somebody that knows wax cube.
We need some more marbles, Clay.
Just got these.
It's dried up. You can't even see that amp down there at the bottom down
We just got these.
Enough dollars from Family Dollar.
Bookstore. Well, these starting off,
there.
baby.
That ain't no belt.
Leave it up or something.
Good. All right. So, see if we can work this problem using that carrier system. So, there, the text we discussed that it has ballpark parameters for what we should expect to see, right? That's probably the hardest part of getting to use this program. Which one to use? Try another one.
You can put it in the box and seal it back.
So, how do I go about figuring out what I should expect from head pressure?
Just add 30. We add 30 to the head.
Add 30 to what?
Temperature.
The ambient temperature where that condenser is. I said it was 95.
Dang.
Plus 35. Man. Thinking Jeff's just putting bad ones back in here and sending them up here. Maybe it's this board material though or something, you know? 25, 35.
Wayne,
You don't get 35, you told us 30.
I'm sorry. Now,
Now
this
you
figure.
were paying attention anyway.
There we go.
And on the new ones, you said 20.
Yes, that's right. The ones in out here in the lobby. Lab. Okay. So, what type of refrigerant we're using? 22. I want to look up 125 degrees 278 pounds. So I expect to see 278. What was it?
240.
So, am I above or below what I expected?
Below.
Low. Suction pressure, okay. Yes, sir.
That's what I got confused about. So the head pressure, that we like those numbers we got on this chart on this side, what you got on this
These
side.
are what you gathered in the field.
Okay, and we always put that to action.
I would put actual, yeah, those are what they really are.
Okay. All right. That
That's
was
what I say. I want expected up top is the second number, which is actual. Is it above or below it? And that's the, whatever it is, that's where you put the error.
okay.
So where we get that actual ten?
You put your gauges on there,
Okay.
and you'd read the high side pressure
Okay.
with it running.
So there we go.
All right.
So you said this side right here, the act of this deal.
Yeah, this is what we gathered in the field.
Okay.
Yes,
Do
sir.
you keep a pressure chart with you for
Not if I got my gauges, I just read it off my gauges. If I'm going to work on, say, some commercial refrigeration stuff, I may print out a chart and take it with me because I don't have that type of refrigerant gauge. Now, the fill piece, it's got about 50 different refrigerants in there, so I can, if I've got that gauge with me, I can filter through and find it. But it still doesn't print up. It tells me, it'll give me the saturation temperature. That's the saturation temperature, right? Y'all follow me? It gives the boiling condensing point. We call that saturation temperature. That fill piece will give me that, but it doesn't have a chart on it. And so, say, I don't want to get too far off the point, but sometimes I want a chart with me. But usually, if I'm using something that I've got a gauge on there, it's printed on the gauge, I'll just read that. Like here, you would look at your pressure when y'all read 240, you would go to the refrigerant color coding, which is usually green for R22, and whatever that temp number was, that's the saturation temperature. All right, what did I say? How are we going to define expected suction pressure?
Core temperature.
Yeah.
You said something about 40 degrees.
I want a 40 degree coil, and so whatever 40 degree is in that refrigerant, right? If I look at 40 over here in R22, that's going to be what, 69?
Yeah.
What was it?
Yeah.
Is this number above or below 69? There you go.
Now,
Yes.
so we went over here and got the 40 then came. Okay. All right. I'm just trying.
And if it was all 410A, I'd look up 40 under 410A. That'd be about 118, 19. This troubleshooting works in all of them. Say I'm working on a reach-in cooler. And I got you. Well, the host will tell me, what do I keep in there? Well, I keep beer in there. I said, what temperature do you like your beer? He said, I want it about 33 degrees. I don't want it frozen. Well, I know that a reach-in has about a 10 degree temperature difference. And a walk-in, okay, 20. So I'm going to go, okay, if that's the temperature of my product, and it takes 10 degrees, coil needs to be 10 degrees below it, I now have a target. And I go to my charts and go, that's the pressure it should be. That's what we're doing here. I want it to be 40, and so I go to look see what temperature it is.
So you can adjust your temperature, like your cooler, based on what kind of pressure you put in it.
Somewhat. You got to remember, we could let some refrigerant out and go from 50 to 40 to 30, but by reducing that pressure, that coil will have that temperature, but it greatly reduces its capacity because it's very low. It may only have 16 ounces of refrigerant in there, so it's only going to pump a little heat. Although it's cold, just a little bit.
Will that mean it works harder? Is
It can only pump a certain amount of volume, period. So if the refrigerant's not in there, it's not going to remove it.
And since it's cold, it's gonna freeze up.
And exactly too there. If it's in coolers and stuff, we're going to have some type of either off-cycle defrost or a defrost method. But getting back to this, superheat. What did I say our target was on superheat?
5 to 12.
5 to 12. And I said it only matters if what? If I got a fix, right? Because if I got a TEV, superheat ain't gonna help.
So you got a TV in that spot,
Then I don't really use superheat to figure it out.
okay.
Only if I'm trying to see if the thermostatic expansion valve itself is bad.
Not fixed, no super.
So we don't get
If we got a fix, cap tube, piston, orifice, then we care. If it's TXV, pardon. All right,
Is everything going to TEV and TXV?
pretty much. It could be efficiencies. How do I find my superheat? What's the formula?
suction
Actual suction line minus saturated suction temp, right? Suction pressure. So my actual suction line was what? 50 degrees. Sorry this is not showing up, y'all.
It was also 50 pounds, wasn't it?
I'm sorry, you're right. Yeah, 50 pounds and 50 degrees. And what was my suction pressure converted?
10
50. Suction pressure was 50. That converts to about 26 degrees. That's going to equal what, 24? All right, I expected 5 to 12. I got 24. Am I above or below my expected? I'm above it. So arrow up. Subcooling. What do we say we're going to use on subcooling? Yes, sir. I'm sorry.
I'm sorry. Can you do superheat one more time?
Yes.
Yeah.
Okay, on
I
here.
got the wrong.
I get 19.
All right, look.
I got 19.
Superheat and subcool are just the opposite. We're going to take, on superheat, we're going to take the suction pressure, right? And on subcooling, we're going to take the head pressure, right? Okay, so
What do we do with that suction pressure?
we're going to convert them to a temperature, both of them. So on superheat, I take the actual temperature minus the converted temperature. The actual temperature minus the converted temperature.
That what you gotta, let's say
Convert-
convert.
Temperature or pressure?
Well, the only way you can get the temperature is to convert the pressure, right?
I thought we had to, Clay, I'm asking, I don't understand.
Okay. This is a pressure. Your gauges gave you a pressure.
Well, we have a temperature also.
You had to take the temperature also, yes. An actual, you took your gauge, your meter, and you hooked a clamp meter and it said it was 50 degrees.
Okay.
You don't understand? Everybody in here got a digital thermometer. You put it on something, it'll read the temperature. We did that on the suction line coming out of the air handler. Do we have that temperature? No. Okay, first of all, I'm losing on somewhere. What is temperature? Everybody know what temperature is? If you put a thermometer in your mouth, it gives you a temperature, a sensible heat reading. There's two lines coming out of the air handler. There's a liquid line going in and a big line coming out we call the suction line. We remove the insulation and we take an actual temperature. That's the actual suction line temperature. Now, you put your gauges in on the condensing unit, right? And it reads pressure. When you read that pressure, whatever it is, in this case, 50 pounds, we would typically like it to read 69 pounds. All right, if we maintain that pressure, which we do, it can turn from a liquid to a gas and a gas to a liquid at that pressure. Just like water turns to steam at 212 at atmospheric pressure. You go up to the top of a mountain, there's less sky on top of it. The pressure is less up there. So what happens? When the pressure goes down, the boiling point goes down. So instead of boiling at 214 or whatever, what is boiling point? 2 what? 212. It drops. Boiling point, condensing point always follow the pressure. 64 boiling point at 109 pounds of pressure. 165 at 455, right? So we got our actual. Our gauge said 50 pounds of pressure. 50 pounds of pressure, R22, turns to a vapor at 26 degrees.
So that's what you do.
How do I convert it?
That's how you convert it.
That's how you convert it. Yes. You find the pressure and look at the temperature.
Then you subtract 26 with 50 with
26 from the 50 in this case.
Yeah,
I'm losing y'all somewhere. Y'all help me.
we got lost on the problem. I mean,
Okay,
Well, okay, maybe it's because it's 50 and 50 we're having a little trouble. But the formula, and again I'm asking, actual suction line temperature or pressure?
Actual suction line temperature.
Temperature,
minus.
and with that temperature we subtract.
The saturated suction temperature is the correct name of it. How do I get saturated suction pressure? I take the suction pressure and convert it with the charter on your gauges.
What you got up there, Clay? Actual suction line, but I can't see.
we can.
I'm sorry, it's actual suction line minus saturated suction pressure.
Suction pressure. And to get that, we take the suction line.
You read the gauges. You convert that to a temperature.
So what? We already have a suction line temperature.
Yeah, an actual temperature, that's right. Y'all may be misconstruing what this means.
Yeah.
Y'all, hang on. So, the line was physically 50 degrees. But going inside, when you look inside that evaporator, because we maintain, in this case, 50 pounds of pressure, when any liquid refrigerant came into that evaporator, it changed from a 26 degree liquid to a 26 degree vapor, and then it superheated up to 50 degrees. That's what happened. It didn't change at 50 degrees. We changed all the liquid to a vapor at 26 degrees. The rest of the heat is superheat. That's just the definition of superheat, right? When I change any substance to a vapor, if you add any more heat to it, we're going to call it what? Superheat. Doesn't have to be refrigerant, it could be water, it could be anything. And at 100% liquid, if I remove any heat from it, that's called subcooling. Look, we got two kinds of heat in this world. Sensible and latent. Sensible heat changes on the scale. 92, 92.3, 92.4. That's sensible heat. But when we change states from a solid to a liquid, or a liquid to a solid, or from a liquid to a gas, or a gas to a liquid, or sublimation, where we go from a solid to a gas, that's called latent heat. I can't, if this is 100% vapor, it can't change to more gas. It's already all gas. So if I add anything else to it, it's going to go up sensibly. And that's superheat. We've already changed all this to a liquid. It can't change more to a liquid. It's all a liquid. And if I remove anything else from it, it subcools sensibly. Okay?
So that's the saturation point.
And when it's changing, when it first begins to change till it ends, that's called saturation. That's right. We can have saturated discharge pressure or saturated suction pressure. But what we mean is it's going through a change. Yes, sir.
Does saturation mean, can saturation be going from a liquid to a gas? So saturation goes either way.
It just means we're not told 100% either way. Saturation is in between, that's right. When we look at an enthalpy chart of R22 in your book, it kind of looks like that. I know.
That's how it looks. Like that.
Oh, man. None of these work. I think it's the board.
Maybe conditioning.
But, anyway, if you could see this, anything over here, right, liquid, 100% liquid. Anything over here is 100% vapor. But when we go through it, we're in saturation. We're changing state. If I'm going this way, 5, 10, 15, 20, 50, and so forth. You know, man, I can't get any of these markers to work on these boards. You can't read them.
They said they came downstairs last night and took a picture of that one, and I think they're scratching the whole project.
So are they going to take these down?
I guess so.
They clean up nice, but they can't read. You can't read what I'm writing.
You're going to get it and the long, whatever else you want.
All right, so
It helps us to award all those.
you got my email, right? You got
It's
my
just going to read for the next 2 weeks.
Okay. So,
Anything else is on the list or not? I don't think so.
superheat. Are y'all close to getting it? And I know this 50-53.
If we just want to learn the formula, we take the suction line temperature, and then we take the suction line pressure
Convert it.
and convert it
That's
to
right.
a temperature, and
I'm sorry. Go.
take that, subtract that from, will it always be with a suction line?
That's a very good question. Well, think about what we're measuring here. We're saying it changed to a vapor in this case, right? It changed in this example at 26 degrees. He's saying, could it ever be 0 or negative? If the only way it could do that is if it doesn't change states. Right? How could the number go down? Well, the only way it goes down is if it's cooling. The liquid's it's subcooling. It would be subcooling if it did that. So, and you're not going to see that. The most you'll see is 0. Probably the least you'll see is 0. Let's think about what this tells me. The air coming over the evaporator hits the refrigerant at 26 degrees. Well, anyway, that's my 50 converted, right?
Yeah.
It's warmer air. It vaporizes it all to a vapor. It goes from a liquid to a vapor. Now it is still warmer than the 26 degree vapor, right? 80 degree air in return, 26 degree vapor refrigerant in the. It's going to continue to pick up heat, right? That's the law of heat transfer, hot to cold. So the vapor has to pick up the heat. In this case, we said it picked up 24 degrees of heat. That's too much. We say, hey, I want 5 to 12 degrees what it should pick up. It shouldn't pick up 24 degrees. Let's move on to subcooling. What do we say our book says that we should have on subcooling?
10 to 20.
10 to 20, thank you. Hey, that one wrote for a second. Now, subcooling is just the opposite. Notice how we had the actual and then the converted flip-flop. So, what's my head pressure? 240. 240 converts to what? 115. 115. Everybody know how we did that? We took the head pressure and converted. So what did we just say? 115? All right, so now I want to subtract the actual, right? Like I said, it's crisscross from the other. And what's our actual liquid line?
95.
What does that equal?
20.
20. What's 20? It's at the edge.
Yeah.
It's the edge of being high. So I'm going to make a little mark here. Y'all see what I'm saying? I may not. Okay. I made an up arrow, but I made a straight arrow because I'm saying I don't know if I want to totally rely on this. Now, before I go on, in the condenser, the compressor pumped hot gas into the top of the condenser. The 95 degree air went over it. It gave up its heat. It rejected the heat to the outside and started to cool down. Once it got down to 115 degrees, it changed state to a liquid. Right? 115 is still higher than the 95 air over, so it gave up more heat. And that liquid cooled all the way down to 95. Everybody follow that? Now, this was outside. What's the temperature outside?
95.
So it couldn't cool anymore. It might have cooled more, but it can't cool off, right? It's the same temperature as the ambient. When's the only time we don't have heat transfer? When there's no temperature difference. And so, although that may not be high, it couldn't subcool anymore. If it was 80 outside, it might have subcooled even more.
So it's doing all it can do.
It's doing all it can do, that's right.
I had air conditioner back then one time. I thought it was lying.
Well, I mean, if it was cooler, it might cool off, but the outside air won't let it.
Can the temperature ever really get down to the outside air?
Yeah, sure.
Okay.
You can subcool that much. Amp draw. What did we say? How we're going to? If it's not on the data plate, how are we going to?
Please.
7
tons.
And this is how many tons?
3.
That'd be okay. So 21. Everybody If I lose you on these, let me know.
Yeah, the Clinton, on that, you see, okay, the outside damper over here is 95, and your, what that liquid line is 95. So we're doing all we can do, right?
How could this be 94? If the liquid line sitting outside was 94 degrees, what's the law of heat transfer? Y'all tell me.
It's gonna go up.
Right, it might have gone to 94 and the outside air brought it up.
Yeah, okay.
That's what I'm saying, we can't go below the outside air. Even if it wanted to. We got, is that 16 amps?
Yeah.
So am I above or below what I expected?
No.
Does this match anything in your book?
No.
I got one question.
Yes, sir.
How did you get the amp drop again?
We said 7 amps per ton, and I had a 3-ton system here. So 3 times 7. Although it's better to use the data on the plate if we got it. Yes, sir.
The suction pressure, I think that's 69 here, with the 69.
I want, for right now, I want y'all always to use a 40-degree coil.
Okay, so 40 degrees.
And so y'all took 40 and went to the chart and looked it up
Okay, so 40 will be my standard for that.
until I change it.
How did you get some cooling? Where'd you get 115 from?
I'm sorry. Head pressure converted. 240 converts to what? It should. Maybe I did my math wrong. 240 converts to around 115, I think.
Oh, okay.
That was like the liquid restriction.
So do you always use 240?
No, whatever head pressure you read. I'm sorry. So what does it line up with, y'all? Does it line up with anything, or 2 or 3?
Liquid restriction.
Liquid restriction. What is a liquid restriction? Probably a filter dryer, right? How are you going to test that in the real field? If I give you a liquid restriction, take the temperature across it. If there's a pressure drop, there's probably going to be a temperature drop.
Also, you could have a TXV feeler bulb charge.
Okay. The reason you eliminated that was because we don't have a TXV. That's exactly right. That's exactly right. All right. If everybody gets this out, let me address this for a minute. Did everybody get one? I know some people came in late. So this is please bring this to class from now on too. This is a chapter on troubleshooting mechanical refrigeration. Now, unlike, we have 5 symptoms we look at here to solve our problems, right? They use 2. You see it says section on page 284, it says 25.2 low suction pressure. On page 284, the first page, the section 25.2 low suction pressure. Y'all see that?
Yeah.
All right, look at the end of it. You go to the next page. It says the following can cause low suction pressure. You see that there's about 9 or 10 things?
Yeah.
Okay. You put your gauges on there and you go, hey, I got low suction pressure. Well, here's what can cause it. Okay. The next section, high suction pressure. Look at the end of it. There's about 10 things. If you get on there and you go, hey, I got high suction pressure, this is what caused it. The same thing with high head and low head. Y'all see that? We're using head pressure and suction pressure only and what they can be caused by, okay? Now, the things that can cause them, we're going to go over each and every one of them. Not today, but we're going to go over every one of those that can cause it. The key to using this system, is knowing, do I have low suction or high suction? Do I have high head or low head? And we should already know that, right? Because I said to use a 40-degree coil on my pressure. And what ambient plus 30 on my head pressure, right? Unless you have better data, like I said, if you got a data plate there that says at this temperature, this is the pressure, that's fine. Okay? All right, so we'll delve into this Monday. We need to,